Hi, welcome back to the channel again. I reviewed this Micsig STO1004 digital oscilloscope in my last video, and I'm quite impressed by the quality and performance of this scope. Be sure to check out that in-depth review video if you haven't done so. And by the way, in that video you probably noticed that the display appeared to be a little bit blurry. Now, that actually was not a problem of the display. I think it is unfortunately a side effect of the matte screen protector used here. The display actually looked quite good in person. Anyway, in this video I will open it up and take a closer look inside. Now, I have to say that this scope is not the easiest to disassemble. The rubber holster is very well integrated and the fit was very tight. And it took me quite a bit of time to actually just figure out how to remove this piece. And let me turn it over just to show you. If you look at the back, you will see that you only have access to this one screw with the holster on. And it is crucial to loosen this screw first so they can pry open the bottom section of the holster and work your way all the way around. Anyway, it took me quite a bit to get it off in one piece. We'll have to see how easy it is to put it back together. Since the STO1004 is based on tablet computer, I fully expect to see commonality between this unit and a typical tablet computer, with the exception, of course, of the front end of these channels and perhaps some dedicated FPGA circuit for this scope. Now, with all these screws accessible, we should be able to open it up. Now, after the back cover is removed, you can see how nicely everything is put together. All the sensitive circuitry are under this metal shielding, so we will have to remove those, of course, to see what's going on underneath. And before I open it up further, I just want to show you the screws used to secure the back cover here. And you can see that these are machine screws. They fit nicely into these metal threads. Removing the main board takes some patience, as there are quite a few flat flex ribbon cables need to be removed before the board could be taken out. And you can see that I also removed this module board, as without removing it, I could not release the touchscreen cable, which was routed in from underneath. I also removed the shielding cam from channel 1 so we can take a closer look at the input section later on. Now, I expect all 4 channels are virtually identical, so I only removed this one. Anyway, as you can see that the board is very well laid out and the design is very clean. Throughout the board, there are many local power supply sections, as you can clearly see via these inductors. And the power chip here appears to be a D9D320 buck converter, and you actually have quite a few of these chips all over the place. Now, because the system is Android-based, I suspect that a significant portion of the circuit is in common with a tablet computer. And you can largely infer that from the bottom portion of the circuit board here. Towards the right here, you can see this chip sitting under the heatsink. I assume that is the main processor. You can also see a SRAM chip towards the left and a flash chip towards the right. Here we also have a battery for the onboard real-time clock. Underneath here we have, by the look of it, ICN6211 DSI video processor chip, which makes sense as it is sitting right next to the flat flex connector to the LCD. Towards the middle section here, you can see this is where we started seeing some of the oscilloscope specific circuitry. Here we have an HAD1511, which is a 8-bit 30 to 1 gig samples per second A to D converter, and that is shared across all the 4 channels. Next to it, we have an ADF4360, which is an integrated synthesizer and VCO. What is interesting is Micsig's use of a SoC module here. What I think is happening is that they actually put the oscilloscope-specific FPGA and associated circuitry on this separate board. If that is the case, it's actually very clever, as it can utilize the main tablet motherboard design and evolving the oscilloscope side of the circuitry somewhat independently. Here on this board, you can see we have some flash memory chip, and we also have this memory controller right here. And this, of course, large one, I assume is the FPGA sitting under that heatsink. Oh, and I forgot to mention, if you look carefully here, you can see that on top of this board we have a UART, by the look of it, port that presumably is used to test the board in production. Now, here is a closer look at the bottom side of the board. We can see a lot of bypass capacitors. Towards the bottom right, you will see that we also have a section that is not populated. Now, if you look at it here carefully, you will see this is probably another LCD connector here. So I assume that in production runs, they may have different models of the LCD, and depends on which one they use, they may choose to populate this section or this section. Now, before we move on to the input section, let's just take a look at the rest of the board here. On this side, you can see we have a lot of these DC-DC converters, as mentioned earlier. And if I move up here, you will notice that we do have a couple sections that are unpopulated. The first area you notice that we are missing some components is this section right here. And here we have, by the look of it, a few ICs and some passives. So not entirely sure what exactly that circuitry is supposed to do. The second area that is missing components is right here. Now, if you look carefully, we do have a trace here. By the look of it, it's an antenna. So perhaps they were designing some kind of RF components here, but not entirely sure. As you will see, I will show you just in a little bit that there actually is a Wi-Fi chip on the other side of the board. And here's another look of the cable connecting the BNC panel to the main board. That, I believe, is for the UPI interface. Now onto the input section. The larger chip here is an OPA 4872, a 12 volts, 500 MHz op-amp with a 4-to-1 high-speed mux. And besides that, there's actually not a whole lot going on this input section here. Now, there is no adjustable components in the input section either. Now let me flip the board over and take a look at the bottom here. I don't think there's a lot going on, but I just want to point out a few things here and there. And here is the backside of the channel 1 input. You can see that we also don't have a lot of things going on here. All these are just some discrete components. And towards the left of the channel 1, we have this AP6181. That is the Wi-Fi module. The shooting cans used here are actually two pieces. One is from the top, one is from the bottom. You can see that here is the one that we took off earlier from channel 1. And this design is actually very good. Otherwise, we wouldn't be able to take them off if they were soldered on. Now move on to the other side. You can see here is actually the backside of that unpopulated footprint on the other side. I suspect it was some kind of wireless communication module. And by the way, these pads here are not your test points. These are actually the board port connectors used to connect to the input section via some pogo pins pressed against them, which I will show you a little bit later. And that's pretty much all there is on the reverse side of this board. And let's just take a look at all these bypass capacitors on the reverse side of the processor. Now move on to the front panel. You can see here is the ribbon cable for the LCD, and here is the touch panel controller. And if you take a look, here we actually have a, by the look of it, a I2C control. And let's move on here. Towards the bottom here, we have two of these speakers. And here is our main controller board for the input section. Let me just zoom in a little bit so you can see the board-to-board connector that I mentioned earlier. You can see these are the spring-loaded pins that is pressed against the pads on the main board. The main controller on this input board is an STM32 compatible microprocessor, as you can see here, and we have a few 595 shift registers here. And that pretty much wrapped up this teardown video. I am quite impressed with the design, and the build quality of this Micsig STO1004 is definitely impeccable. Certainly hats off to the design engineers. Anyway, I hope you enjoyed the video and learned something new. If you liked the video, please remember to give it a big thumbs up and remember to subscribe to the channel for more videos like this in the future. I will catch up with you next time.